and welcome to my Traveling Salesman Problem Complexity Visualiser. In this video, I shall be demonstrating the functionality of this system. Okay, here we go. Firstly, this system has start and reset buttons. The start button runs whichever algorithm is currently selected in the drop-down box. So we select nearest neighbour. It's going to run this algorithm, and it's going to output the result. We have a reset button, which clears the total cost of this route, and it clears the route from the graph. Here we go. We have a drop-down box, which when clicked, it shows you the list of the 4 different algorithms: nearest neighbour, convex hull, chopped inversion, and brute force iterative. We have, and you can select an algorithm, and it's then a selected algorithm. We have the total cost label, which describes the total cost box, which displays the total cost of a route. There we go. Then we've got a new graph button. This button clears the route and the cost and the graph, and then it creates a new graph on the display. We have a slider above it, which determines the number of vertices in this new graph. So if we put the slider quite a small number, then we get a small number of vertices in the new graph. And if we put the slider to a large number, then we get a large number of vertices in this new graph. Okay. Right, let's just display a route, an algorithm. And you'll notice that while an algorithm being displayed, each edge is shown edge by edge in red, and then when the algorithm is finished, it's shown in green. Just demonstrate that on a smaller graph. We run each edge is shown edge by edge in red, and then when finished, it's shown in green. Okay, let's demonstrate some of the algorithms. We have the convex hull algorithm. This is a circular algorithm, so it creates an outer circular route, and then joins up all the vertices that weren't created to that outer hull. So it works something like this, taking this outer loop sort of thing. So originally it would have just looked something like this, from here to here to here to here to here to here, and then it's joined up this vertex here, it's joined up this vertex here, and then it's joined up this, and it's joined up this vertex here, and then the route has been formed. We also have the nearest neighbour algorithm, which always takes the next shortest edge. So let's say it starts here, it's then going to go always to the next shortest edge. So you can basically very easily predict where it's going to go. And it creates a nice little route. Then we have the 2-opt inversion algorithm. So this is an improvement algorithm, whereas nearest neighbour and convex hull are constructive algorithms. Constructive algorithms means they don't take anything as an input, and they create they use heuristic methods to create like an initial route, but it's normally not optimal, and they're quite quick. 2-opt inversion takes in this final route of a constructive algorithm and tries to make small little changes by finding similar routes, and if those small little changes improve it, then it keeps that as the new best route. How 2-opt inversion works is it takes every single edge and compares it with every other edge and swaps those 2 edges, and if the route is improved, then it keeps the new route at any point. So to demonstrate that, since nearest neighbour has been run last, when I run 2-opt inversion, it would take in the nearest neighbour route, and then it will try swapping all the edges and improving it. Let me just create a slightly bigger graph, because on the smaller graphs, the nearest neighbour is already quite efficient. Whereas this, we can see here, there's this long edge along the bottom, which we want to get rid of that, and we want to get rid of this long edge that goes through the graph. So if we run tilt inversion, going to see that it's going to have, oh wait, it hasn't got rid of this. It hasn't found a better solution, but it has got rid of, it's rearranged the root over here and made that a lot nicer. The reason why it doesn't always fix some of these crossings is because it's, if we run the nearest neighbor over the top, we can see that it did flip this this long route to a different one. So the long edge did actually change. It changed from this vertex to this vertex. But if you were to run tilt inversion again on this route, then it would change this edge again, and hopefully go to this vertex here. But that's okay. It's not supposed to be perfect. It's a heuristic method to kind of quickly approximate a good route. Not claiming to get a perfect route. Then we have the fact that tilt inversion takes in the last used constructive algorithm. So if we now run convex hull, which is, it's really liking this circular. It's created an inner circle around the outer circle. It's okay. Tilt inversion is going to take in this last used route, and it's going to try swapping edges and try improving the route. So here, this is a better route, and we can always see it's a better route because the total cost of every route is always displayed up here in the total cost box. So we can always see it's improved the route, and it looks better as well, of course. If I run convex hull over the top, you can kind of see that it's a similar route, and you can kind of easily observe the changes. Unfortunately, after the route's finished, they both come in green, and this makes it very hard to distinguish which route is which. So if I was to redo this project again, I would definitely have each algorithm finish in a different color so that you could overlay them and easily compare them. But it's the thing. You always learn things from doing a project, and it's hard to know everything at the start. We're also now going to talk about the fact that tilt inversion takes in a convex hull, a constructive algorithm if a constructive algorithm was ran before it run. But if no constructive algorithm has been run, whatever. So let's say you create a new graph and you run tilt inversion for the first time, then no constructive algorithm has been run. Then it defaults to solving the nearest neighbor algorithm and then improving the nearest neighbor route. So like on this graph here, it will. If we run tilt inversion, you'll now see that when I run nearest neighbor over the top, it will be quite similar because it has used the nearest neighbor route as the initial guess. Another test you could do is you could run tilt inversion, and then you could run tilt inversion again, and since the previous route isn't constructive, there is a previous route, but it's not constructive, it's not going to take in tilt inversion, this solution, as its input. It's just going to use nearest neighbor again, which means it will just default to running the same thing. Another the way you can see this is if you run convex hull. That's the convex hull. Then the tilt inversion takes in that and improves it. But then when you run tilt inversion again, it's not going to improve this route. It's going to default to the nearest neighbor route and do that. Okay, then we have the brute force algorithm. This is an iterative solution. So it generates every combination of route and then compares them all and selects the best one. Since there are n-1 factorial combinations on a graph of this size, it would just take way too long. So we want to use a much smaller graph, and then it's just gonna output the nice solution. It can do a graph of like this, 8, quite quickly. It can do slightly bigger actually. I think it can do up to 10. This is too big. But this is 10. This is good. It should take maybe 2-3 seconds, and then it outputs the route, and you can see this is always going to be the best route. It's really, really nice. And there we go. So it's a low total cost. And you can always compare it with like the nearest neighbor. You want to see, okay, the nearest neighbor is slightly worse, but then after inversion, perhaps that is the optimal route. You can see 3085, and then when we run the brute force, wait like 2 seconds. It's then also 3085, and you can see it's the same route. So nearest neighbor plus topped inversion gives you the optimal route on this graph, which is quite a cool thing to observe. Okay, now we're going to test the inputting from a text file. So all the free text. So to input from a text file, the text file must be in the folder of the solution. It must be in the debug .NET 6 path. The content, all 3 files that I have in there currently are called matrix input problem, and then they are 1, 2, and 3. The contents of these files can be found at the bottom of the at the bottom of the testing section in my report. Okay, let's just start. So the first graph, matrix input problem 1.txt, is a 8x8 graph. Okay, it's going to work by showing the total cost here 32, and that's used the brute force iterative because that was the selective algorithm, and then it's shown as the route the brute force has taken to get this minimum cost of 32. And since it's an 8x8 graph, there's 8 vertices, so the vertices are numbered 0 to 7. So it's saying go from vertice 0 to vertice 2, and then from vertice 2 to vertice 3, and then from 3 to 1, and 1 to 5, and then from 5 to 7, 7 to 4. And then here it said, okay, to get from 4, we want to go back through 0, and then to 6, and then we want to go 6 to 0, and that's the most efficient route. So we can try it with something like nearest neighbor as well. And nearest neighbor, because it's a small graph, nearest neighbor also finds the same minimum route or minimum cost of 32, but it's actually found a different route because since it's a weighted graph, there are actually different routes that get the same cost. More common. Okay, then we have matrix input problem 2. This is a 6x6 graph, so we'll run the nearest neighbor on it, and it will give us the route with total cost of 33. You can run 2-opt inversion as well, and this will do the same thing, checking the different edges, just like the visualizer. But it's found the same route, which means that it found no changes, which is okay. In the brute force, now we will find out if this is the optimal, and it is. It's fairly free. It's found a different route, but it's probably because there's quite a few routes that give a cost of 33. Now our last input problem is input problem 3. This is in the wrong format, so there are maybe not all rows have eight numbers for the weights. Even if there's no edge between 2 vertices, there should still be a 0 to show that. Or there's not commas in the right place, there's 2 commas next to each other, there's some sort of syntax error, and then it will say no file in correct format detected. And if you were to just enter some random file that doesn't exist, it would also say no file in correct format detected. And if you were to just click this button without actually entering a file name, then it would say no name detected. Thank you for watching my traveling salesman problem complexity visualizer. That is all. That is very cool. Let's just watch one more brute force. Yeah, that just looks great, doesn't it?